Okay, so Le Chatelier's principle, now let's put some numbers on it. Le Chatelier's principle, of course, says that the reaction is always moving toward the equilibrium state, which of course makes total sense. So how do we do this numbers wise? Let's take an example reaction, and I'm not gonna, we're just gonna do a really generic example. Let's say that we have a reaction that's A plus B creates 2 moles of C, right? And furthermore, I'm going to tell you that the KEQ of this reaction equals 75. Right? So absolutely just made up numbers, but here we go. So we know what the KEQ of this reaction is. We can write out the KEQ expression as well. KEQ expression equals concentration of C squared over the concentration of A times the concentration of B. Right? So we have that. We have the KEQ value. What this means is that um, when we are at equilibrium, when the reaction reaches equilibrium, these two things are equal, right? The concentration of C squared over the concentration of A times the concentration of B equals 75. When the reaction is not at equilibrium, right, then we know that it's going to move toward this number. So let's do an example where it's not at equilibrium. So at some time, right, at some point, somebody measures the concentrations of each of these things and says that the concentration of C at this point is 1.2 molar. The concentration of B is 0.03 molar, so there's not very much B remaining in there. And the concentration of A is 0.5 molar. And so we look at this and okay, there's not very much B in there. There's a lot of C that's in there. What's going to happen is, so what we want to find out is which direction is this going to go? Will this, from this point, will this reaction produce more product or more reactants from this point, right? And the way that we answer that is we find Q, right? So what Q is this expression, the concentration of C squared over the concentration of A times the concentration of B. But the difference is that Q, our reaction quotient, Q is this value when the reaction is not at equilibrium. So now all we need to do is just plug in these numbers and we can calculate Q at our particular point, right? We take 1.2 squared divided by 0.03 times 0.5. And that gives us 1.44 divided by 0.015 gives us a value of 96. Okay, so our reaction quotient is 96, right? And our KEQ is 75. So in this case, Q is greater than KEQ. So what does that tell us? That tells us at this point in time, the numerator of our expression is larger than the denominator, right? Or is, I guess, is more large, is more larger than the denominator than we would expect at equilibrium, right? Because Q is greater than KEQ, that means that we have more product than we would expect at equilibrium. Q is greater than KEQ, more product than we would expect at equilibrium. And so, therefore, the reaction will move towards equilibrium by producing more reactants. Right? Because to balance this number out, to turn 96 into 75, we need to make the denominator larger. Right? And so that means that we need more reactants present in our reaction. Okay, so what happens now if we take those same concentrations? Concentration of C is is not 0 point anything, is 1.2 molar. The concentration of B is 0.03 molar. And let's say that we add a little bit more A. Right? We add we get this up to 0.7 molar, right? So what we've done is we've added more A to the reaction from slide 1. You know what's going to happen, right? Le Chatelier tells us what's going to happen. If we add more reactants to our reaction, what is that going to do? It's going to push the reaction toward more products, right? So we can do that numerically now too, which is what I'm going to do next. So we calculate a new Q, right? Q in this case is 1.2 squared over 0.03 times 0.7. 1.44 divided by 0.021 equals 68.6. And so now, of course, we have Q less than KEQ because KEQ was 75. And so the opposite thing is going to be true in this case than it was in the previous slide, right? So now Q is less than KEQ. That means that there are more products present, or more reactants present, excuse me, more reactants present than we expect at equilibrium. And so from here, the reaction will produce more products. Right, in order to get to 75, the KEQ of 75, we need to produce more products. So this is how we do this, right? We use Q as a reaction quotient. So Q is basically the KEQ expression at some time that's not equilibrium. So if you're at equilibrium, then you are at KEQ, right? You use the expression and that gives you your thing. If you're not at equilibrium, if you use that expression, you're going to find Q and that tells you which direction you're going to go, right? If Q is less than KEQ, you produce more products. If Q is greater than KEQ, you produce more reactants. All right.